Good evening, everyone, and welcome to our today's session. I am Anali Chakraborty. At the outset, let me thank you all for present here today. It's a great pleasure for me to introduce our speaker today, who is going to talk to us about radar detection and stealth technology. The eminent speaker of this wonderful topic is Dr. Chandra Bakshi. He is currently a senior member at Institute of Electrical and Electronic Engineers, and he is serving as assistant professor at National Institute of Technology, Calicut, Kerala. He received PhD degree from the Indian Institute of Engineering, Science and Technology, Shibpur, Howrah in 2021. From 2014 to 2015, he was with ISRO, Ahmedabad, India, where he had worked extensively on phased array and reflect array antennas for satellite communication with the Antenna System Group. During 2022 to 2023, Dr. Bakshi served as a postdoctoral researcher at the Department of Electrical and Computer Engineering, National Institute of Singapore, where he worked on flexible phased array antennas for satellite communication and various beamforming techniques. In 2023, Dr. Bakshi worked as an employee of university's research at NUS Environmental Research Institute. He is interested in various applications of FSS for radar and stealth technology. He has published numerous high-impact journals articles in the relevant topics. He has appeared as the most accessed article in IEEE Transactions on Antennas and Propagation in 2021 for the paper Multifunctional Frequency Selective Resolver with Dual Modes and Continuous Tunability. And he is the pioneer of the field of tunable resolver. Dr. Bakshi is the winner of the prestigious Warner Grain Foundation's tax-free postdoctoral fellowship 2022 for education in Sweden from the Cutthroat International competition held by the Warner Grain Foundations. He had also secured numerous postdoctoral fellowships from prestigious institutes like Stockholm's University, Sweden, University of Westloo, Canada, Carleton University, Canada, Concordia University, Canada, etc. He had received the Best Paper Award in INCAP 2019 and also Best Reviewer Award from Elsevier. Dr. Bakshi is an active member for the education community of IEEE, Electromagnetic Compatibility Society, where he is responsible for developing course material for global study. He also served as an expert and then was elevated as full member at IEEE Antenna and Propagation Society WG2 Quantum Sensing or Imagining. Now I request to Dr. Bakshi, please start your deliberation.
Thank you very much for your kind introduction. Am I audible? It's clear?
Yes, sir.
Yes, sir.
Please turn on your camera.
I don't have camera here. Sorry, I'm doing it from home, so I don't have camera. Is that fine?
Okay.
Uh, can you see my screen here?
Yes.
Yes, sir.
Okay. So before starting it, the topic is quite technical, but before that, I would like to know that how many of you are from engineering background, especially from electrical engineering or something? Or most of you, what is the audience from? Hello, am I audible?
Yes, sir.
Uh, okay, so the topic is radar detection and stealth technology. I'll
Excuse
try.
me. Excuse me. Is it possible to turn on your video?
I said my camera is not here. I'm doing it from my home system.
Oh, okay. Okay. Thank
Yeah. So, can you see the screen?
you. Yes, sir.
Yeah. Okay. So the topic is the radar detection and stealth technology. So what we are going to do is to discuss the basic principle of radar, how exactly it works, the types of radar, and then we'll be going to stealth technology. Stealth means hiding of an object from the radar. Although the topic is bit technical, I've tried to make it accessible to person who are not even from engineering background. Let's see how is it possible. So this is the table of contents. So first we'll go through the radar working principle, how exactly radar works, then the application. Then we'll briefly try to discuss the types of radars. And then especially we'll going for the Doppler radar, it's a very important application. Then we'll come to stealth philosophy. What exactly stealth philosophy and radar cross section is that the stealth philosophy deals with the hiding of object. Mainly radar system is for detecting of the object and the stealth philosophy is hiding of object from a radar. Then I'll try to show you one or two works which we developed in our laboratory to for stealth technology. There will be many slides which will be a bit technical, so we'll be omitting that slides and try to discuss the more things, more physical perspective, so that it becomes accessible. So what exactly a radar is? It is radio detection and ranging. That means this radar actually uses radio wave, whatever radio wave, electromagnetic wave, your mobile signal, and all this comes from radio or electromagnetic wave. Radar uses radio wave for detection. Detection means an object detection, whether any object present or not. And ranging. Ranging means how far the object is from you or whether the object is moving, what is the speed and velocity. That is the main motto of the radar. So before going to the radar, I would like to tell many examples. You can see that, for example, whenever in a aircraft, be it a civilian or be it a fighter aircraft, whenever it is moving, you see that always it is being connected with the control room. The pilots are getting connected with the control room. Everywhere from the control room, the presence of the aircraft and everything is monitored. How it is monitored? Once aircraft goes above the our level, like 5,000, 6,000 feet, everything, all of this kind of monitoring is done by radar because you cannot see the aircraft. So anything which is like, for example, other things like missiles and whenever you send missiles to 1,000 kilometers, 2,000 kilometers apart, how can you monitor? How can you see that whether it is going or not? Everything which you cannot see directly, but you can use radar for monitoring that. Another advantage is that radar uses electromagnetic signal that I said. I'll come to the details how exactly it works. So the benefit of radar is that electromagnetic signal, ideally the velocity of the signal is the equal to the velocity of light. So that means when whatever signal you will using, that will be extremely fast, quite to the close to the velocity of light. So the detection is almost instantaneous. Okay, almost instantaneous. It is not like sound. So that detection is almost instantaneous. So as I said that initially radar in 30s, 1930s was first used and first started, and the idea was to detect the hostile aircraft system. In the year of 47, 1947, radar started getting its application in the civilian purpose as well, like speed measurement of car. Whenever you see that you are driving car or you're going cars in a highway and see that in digital meter you are getting your speed, in what speed you are going on. That actually done through radar. There are also small radars out there. Radar frequencies is like generally in different X-band frequencies, X-band means 8 to 12 gigahertz. That frequency is used. Other frequencies are also there. I'm not going to these things. And around 1972, moving radars were also discovered. So this is the radar principle, how exactly the radar works. See, this is the target and there is a transmitter receiver. That is the radar system. What happens is that from the radar, different kind of waveforms, say continuous or pulse, electromagnetic signal is transferred from the radar, just like from any antenna. This signal goes to the target, and as the from the target it gets reflected, and when it gets reflected and come back to radar, it is received. So by this received signal, radar can determine whether any target is present. If no target is present, no signal will be reflected. It can also determine by the calculating the change of phase of the signal or by changing the Doppler shift or the frequency of the signal, whether the target is moving, in which direction target is moving, whatever velocity in the target is moving, everything can be determined. So this is all the radar. This is the basic principle. Some signals should be sent from the radar and it should get reflected, and then when it is returned back from the after reflection, after collection, the pre-processing. That is the system, whatever radar, be it the oldest radar or be it the most modern quantum radar, this should be the basic idea. So that's exactly what I said. Just you can just see that some fighter aircrafts are moving, and from the radar system, in the radar system, the last part will be the antenna, from where the signals will be transmitted. From the antenna, some signals are being transmitted, and these signals go to, if you see this example, this is the last antenna. From this antenna, some signal will be transmitted. It will go through the hostile aircraft, getting reflected, and will come back, and it will then process. Then you can identify that position and speed of the hostile system, and by this preventive actions will be taken. Most of the cases, radar send high energy signals, so the reflected signal has got enough energy so that it can get detected. Another application is to measure the speed. To measure the speed, actually what happens, because whenever the signal is getting reflected, you can identify whether the target is present or not. The next question is that to identify that, what is the speed or to estimate the speed of the target. So to estimate the speed, there is an application of Doppler shift. Some of you might have read this Doppler shift. That application, that use of theory is used. How to use this? What happens is that whenever the reflected signal, say you are sending a signal at a particular frequency, you will getting the reflected signal to somewhere shift of the frequency. Either it should be the higher or the lower than the transmitted frequency. As you are the radar designer, you know that in which frequency you are transmitting. But whatever frequency you will be receiving in the received signal, that will be either higher or lower. Now, from the Doppler principle, I'm not going into the principal details. If the higher the speed of the object, the higher will be the pitch, and the lower the speed of the object, the lower will be the pitch. Now, the radar in its display will be able to calculate the target speed in mile per hour, and will be generating the Doppler tone. So that is actually how in the submarine also things works. By using Doppler shift, the submarine also determine that whether another object, is it another submarine, is it a ship or something else. Everything is determined, can be determined by the speed. Say some other submarines are there, then there should be some speed limit. If some boats or some other metallic objects are there, the speed limit will be different. So by understanding the higher and lower pitch level, the speed is determined. So now the question is whether anyone can design a radar. The answer is there are typical regulatory authorities are there. They have given some sorts of rules and regulations to determine radar. Why these rules are necessary? Because if someone designs a very high power radar and that radar signal may cause harmful effect to the human, may cause harmful effect to the environment, and other principles are also there, like different bands are sometimes reserved for different applications. So there are 3 international regulatory bodies are there. They have given a set of rules and regulations whenever you are designing or any company is designing a radar system, they need to follow this. So this is typical bands of radar. Possibly you have heard about this, like VHF, UHF radar. For low frequency, like first 2 VHF and ultra high frequency, As the frequency is low, from the physics, you know that the wavelength will be high. So for the high wavelength, due to the large high wavelength, it will be useful for detecting object which is present very far. So this is used as a long range surveillance radar. As you go on to the frequency like X band, you can see 8 to 12 gigahertz. As the frequency increases, gigahertz means thousand of hertz. So gigahertz is far higher than megahertz. If you go to that high frequency range, then that signal will not travel very fast, very long. So what happens is that you cannot detect an object which is far behind. But what is the benefit? The resolution is increased. That means you can get a very accurate information about the speed and velocity. So that's why every country has got a series of radar systems. VHF and UHF radars are used to determine whether any aircraft or system is coming from very far end, and whenever it is coming very close, then continuously L, S, C, and S-band radar starts working to accurately determine its speed and velocity. And also recently 40 to 100 gigahertz millimeter wave radars are also being developed, but all of these are in the experimental phase. I'm showing you some examples of radar. This is aerial target rotating radar in the left. We might have seen this. Generally in Air Force stations, this kind of radars are used, and you can also see this will be mechanically rotating 360 degree. If you have gone to any airport also, you'll be seeing some radars are continuously rotating so that they can get a full 360 degree view of that. Another radar that you can see is that weapon locating radar. This kind of portable radars are placed in heavy vehicles, and generally they are put in our border areas to locate exactly where are the position of the weapons in the enemy side. So that is why this kind of portable radars are also used to identify in the other side, in the border, opposite side of the border, what are the positions of the weapons. Another example, this is a marine radar. If you have seen large ships, you have also seen this. The top white part of these things, this is 360 degree rotating. You will see that continuously these radars are rotating. What happens when you are in ship? The ship, they cannot see very far. Okay, so the only radars from the radar system, they can see that within 20 kilometer, 30 kilometer, 40 kilometer distance, if any other ships are present, in which direction they are coming or no. So these are very high power radar, generally very low frequency, high power radar, and its sides are also very high. And to get a full view, so that 360 degree all sides, these radars you will see continuously it is rotating. So in marine also you can see the application of this kind of radar system. Another two examples, they are very interesting right now is using. One is ground penetrating radar. This kind of radar is like small card like things. What happens in sometimes enemy put some kind of detonator or bomb out within this soil level. So before sending to a convoy of army or convoy of any other important, you also have seen sometimes whenever VIPs are going to any road or something, this kind of GPR are being used. The idea is also same. From the GPR, electromagnetic signals being transferred to the soil, and it goes inside the soil and get reflected. From the reflected signal, it is processed and to determine whether any other object is present in the bottom or not. The same idea is also used as a thorough wall radar. You can see, for example, in a very thick or large wall is there in hostile system. You cannot go inside there. You cannot see what exactly things are there inside. So to identify the target, what happens? This TW radar is used, thorough wall radar. This radar is capable to determine that what is there. The same thing happens. Electromagnetic signal. This is the benefit of the electromagnetic signal. Unlike light, it can pass through any object. If it is metal, it will be getting reflected, but if there is any other object, it will be passed through this. So the electromagnetic signal from the TW radar will be passing through the wall and enter in the opposite side and get it reflected. From there, the system can identify, or system can show whatever objects are being present in that site. So now I'm coming to little advanced thing, types of radar. Basic kind of radar is the monostatic radar, and monostatic radar means only one radar sends a signal to the target, and whenever it is getting reflected, it collects. Bistatic means, bi means two, but multistatic is also possible, where one radar system sends a signal, but multiple of radar can be used to detect the signal. The benefit becomes, if the target reflects signal in other direction where the main system is not present, then the chance of getting the target undetected reduces. Whenever you send a signal to a target, in whichever direction it radiates, it can be collected if a multistatic radar is used. This is another kind of radar. This is called a pulse radar. Pulse radar means instead of sending continuously electromagnetic signal, some electromagnetic pulse are sent to the system. The benefit of using pulse radar is that you can actually calculate the time delay by which the signal starts from the radar and when it is getting reflected. And if you know the time delay, you can really understand that exact distance, at what exact distance the object is present. Because the signal is actually traveling twice the distance present from there, and it is traveling to the velocity of light. So if you can get the time by which the signal getting reflected, you can understand that total how much distance it is traveled. So half of that distance is the distance from the object from your radar. So this sometimes that pulse radar are used. So also there are different types of pulse radar. I have only shown you a very simple pulse radar. But the basic idea is pulse radar is that instead of sending a long electromagnetic signal, some small electromagnetic pulse are being sent. This is the underlying principle and the internal circuit of pulse radar. I don't think that will be much relevant for you. Let's omit this. Now let's come to continuous wave radar. This kind of continuous wave radar, you can see that continuously it transmits signal. You see the transmitted signal, it goes to an aircraft and getting reflected from the radar. So this continuous wave signal, you cannot calculate the distance from the, let's like pulse radar, that whenever signal is traveling and whenever signal is receiving. But in continuous wave radar, first of all, there are advantages of continuous wave radar. First advantage is that in pulse radar, there is a chance of object missing. Say, for example, you are detecting one object and by this time another object comes. So by the gap of sending one pulse to another pulse, the object may get undetected. But in case of continuous wave radar, you are continuously sending signals. So there are chances of getting object undetected reduces. And this received signal, you can see that if you see the type of the signal, the drawing you can see, if you know the frequency, the signal frequency of the transmitted and received signal is different in case of continuous wave radar. This system calculates the change of frequency and the change of phase shift to understand how far the object is present and how exactly it is operated. I'm also showing you another example of this continuous wave radar. So you see, this is some typical result of a warship that you can see. This is the pulse radar transmission and this is continuous radar transmission. If you want to know that what kind of radars are necessary, both kind of radars are used. Pulse radar, continuous wave radars are used to identify the object and its speed, and when it is identified, then pulse radars are used to accurately determine its distance position. So that is why a radar system kind of things are formed. Different kind of radar has got different applications. So you see that warship, why it is so heavy, is full of different kind of radar system, which some radar system determine the presence, some determine the speed and velocity, some determine the size of the object. So different radar system will do different work in this particular scenario. Another detailed discussion of the pulse radar. You see, I'm trying to make it a little simple. There are two pulses. Previously, I have shown you some different pulses. Here are another different types of pulses. So these square waveform pulses are being used. This from transmission, it sends back to the aircraft and it is getting reflected to the receiver end. So by the difference, that is the separation from the pulses, you can understand that how much gap it is taking from sending a pulse and receiving a pulse. But if it is a continuous wave radar, you will see this kind of waveform will be generated because it will be a continuous transmission and from there receive some ghost signal will be there. So you can also calculate the packet, number of packets sent and all these things, but that will be the little bit of advanced thing. I'm not going into this, but the basic things you can see that this is how exactly the pulse and continuous wave radar works. Now, one interesting principle is Doppler principle. That is, Doppler discovered the relative motion causes signal observed frequency by change of starting sound waves. Actually, it was studied for sound waves, but definitely it also applies to electromagnetic wave. That is exactly what if the object, now your target is not only detection of the object. See, it's a hostile aircraft. you cannot afford only detecting the hostile aircraft. You have to understand at what frequency the aircraft is coming, in which direction it is going, and all those stuff, so that you can use your missile system to destroy that. So for that, Doppler principle is used. What happens is that, as I previously shown you, that whenever you transmit some signal, maybe a continuous signal, and when it is getting reflected and come back, the change in frequency of the signal from that, you can identify by applying Doppler principle that in which what is the relative motion of the two systems. Now, relative motion, if you have studied class 11 physics, you know that if the two objects are moving, then what is the relative motion? If both are in same direction, that will be added. If in the opposite direction, it will be subtracted. If they are in different direction, then you have to take the vector subtraction. So that is the Doppler principle in 11th standard physics. It is. So this, by using the Doppler principle, you can identify the relative velocity. And here benefit is that your radar system, if it is a stationary radar system, its velocity is zero. It is an stationary system. So you can understand that at what frequency, or in what speed the other objects are moving and in which direction they are moving. Another typical example I'm showing you, this is a weather radar. This is also a Doppler radar. All kind of weather forecast and whatever you see, that is also done by radar system. This is a very large Doppler radar. What happens here? Electromagnetic signals are sent and it gets reflected from the cloud. From the cloud, it gets reflected. Change the frequency occurs. By this, the authority try to understand that where the clouds are present, in which direction they are going, what is the depth, what is the thickness, and all other parameters. So this kind of Doppler radars are not only used in defense application, but right now whatever weather forecast and whatever things you are seeing, that are done by this radar system. You might have seen this kind of Doppler radar. You can see this radar in different places where weather forecasting is done. I'm showing you the Doppler principle. I'm trying to show you the Doppler principle in a little easier manner. If the object receding, then the wave appears longer. That's the redshift. That I show you that here the frequency, that is the frequency is decreasing, but where this is blue shift, that is object approaching to your system, in that case frequency is increasing. The time periods are decreasing means frequency is increasing. This is the intuitive understanding. So this frequency means reflected frequency. Transmitted frequency, you know, because your system, you are generating the frequency. In case of reflected frequency, whatever from the red shift or blue shift, just as for namesake, it has been given. Whether the frequency is increased or decreased, by this you can identify that the from the Doppler principle, you can identify the speed, object velocity of the object, and the direction as well. This is another example of Doppler. You cannot see the radar system in your real life, but what you can see is that maybe from a car or something, you are getting a signal, and if you come very fast to the observer, or if you go away from the observer, the same thing you can hear. Because as I told, the first Doppler principle was invented by sound wave, but sound and electromagnetic wave, its property is same, exactly same. So if you are moving towards the observer, or if you are coming far from the sound, you'll be able to understand that what exactly Doppler. You'll be hearing the different pitch of sound. That is actually the change of frequency of sound that you can see in your real life. This also I'm not going. So right now, actually, for automotive radar systems are developed for automatic cars with driverless car. For that also, this Doppler principle and Doppler radars are being used. Not going into this. Let me show you this for weather radar, how exactly it works. So you see that, say for example, for a very long distance, very large distance, some rainfall is happening or from clouds are being accumulated. So this Doppler radar, as I told you, it sends electromagnetic signal and gets it reflected. So if rain is happening or if the clouds are present, then the reflected echo frequency will be different, because thickness of the clouds will be higher. If the clouds are present, a higher thickness will be there. There will be lower frequency shift in that case. And if the weather is completely clear, no cloud have been accumulated for 300, 400 kilometers apart, then the signal frequency will not be more or less unchanged. It will be not unchanged as an ideal, but more or less unchanged. From this Doppler principle, actually, this you can identify that clouds are present or not, whether precipitation is there, how much rainfall is happening, and from this you can predict exactly Why? How we can predict? As I told you, from the relative velocity, you can also identify whether clouds are moving towards this or clouds are moving towards another side. So you can predict the weather. So weather forecasting, for that weather forecasting also, this Doppler radar has got tremendous application. Now I'm coming to stealth philosophy. What is stealth philosophy? Stealth philosophy means when the radar systems are developed at the, this is mainly started being used for defense. So whenever the electromagnetic signal goes to the aircraft or something getting reflected, the aircraft you can detect. Now this stealth philosophy is, if you want to send your aircraft to a hostile territory and want it not to be detected by the radar system, then what to do? That is the stealth philosophy. It is the counter attack technology. That means you design your system in such a way so that it doesn't get detected by the radar. So that is the stealth philosophy. So you see here, if you can make a system aircraft like that, if a signal goes to it, it doesn't get reflected, then your system will not be detected. But this is not an easy task. Till date also, this stealth aircraft is not fully developed, except F-22 Raptor or something which US has developed. Other systems, stealth aircraft is very difficult to develop, because your aircraft also, you have some transmitting antennas and transmitting receiver. So it is difficult, very difficult. But we'll be showing some typical examples how you can design this. This is a plot of radar cross section. This is the aircraft you will see in the front and back side. The higher part means from there higher reflection is there. Whenever radar wave impinges, higher amount of signals will be getting reflected from there. From the wing side also, as the metal is higher, the reflection is much higher. So this is how a signal system will look like by the radar. It will see this kind of waveform. It will not able to see. It is not a common human, so it will not able to see the aircraft, but it will be able to see the reflected output, and from the detect process that this kind of aircraft is present. So that is how the radar system looks like. So what exactly the radar cross section? Radar cross section is, if it is a conventional aircraft, what I have shown, that is a commercial aircraft. That is a not, we don't need to hide it from the enemy territory or something. So if you see the front side of this aircraft, you will see like this kind of front, because signal will be there and it will be getting reflected. But stealth fighter, you'll see that some different designs are used, so that if the signals are even impinged on the stealth fighter, it should not get reflected to the radar system. Sometimes in the example I have shown that after impinging the signals are reflected in other direction. So if it is reflected in other direction, the radar system will not be able to detect. But that is only possible for monostatic radar. If you use bistatic radar, that is multiple radar will be used in different places, then it will be again getting detected, because in some direction the signals are being reflected. It may not be coming to your own radar from where the signal is transmitted, but it can be get detected to other radars. That is why a series of radar, kilometer-wise distance series of radars are placed in LOC areas, so that whenever any aircraft from the hostile system is coming, you can get it detected. So the main concept of RCS or radar cross-section is that you have to design your system in such a way. First, it should not, whenever any signal impinges, it should not be reflected to your radar system. And if it is more modern, it should not be reflected to any direction, so that your system remains completely undetected. So I am showing you one particular application of this stealth technology. This may be a little bit of difficult for you to understand at this stage, but still I'm trying to design. I'm trying to describe what exactly it is and not take much time. Try to say it briefly. What happens is that in order to help your aircraft undetected from the radar systems, generally, in initial days, some coating materials were used for aircraft, or some other coating devices are used. The idea is that whenever electromagnetic wave falls, the coating material will be absorbing the entire electromagnetic wave, so that there is no chance of reflection. But the problem is that whenever you are running an aircraft in your territory or even in a hostile territory, if you do this kind of coating kind of thing, then you also will not be able to communicate, right? So you will also be completely isolated from the other aircraft or from your base station. So that is exactly not possible to do. In that case, who will be will be guiding your aircraft systems. So that is why a new technology called radar absorbers, which is specifically designed absorber for radar system, is being developed. You just see this figure. S11, S21 means reflection and transmission. So if the reflection is high, you can understand that it will be detected. So the main idea is that instead of going it in S1 or S2. And the main idea is that for a wide range of frequencies, if you can design a system in such a way that whenever signal gets impinged, it gets absorbed, so it doesn't get detected. But if you can give a very small window of frequency where you can communicate, then the problem gets solved. So that is exactly called radar embedded communication, and that is for reservoirs are being developed. So I am going to show you one work which was a collaboration between Ohio State University, USA. So that was the angularly stable broadband reservoir. Angularly stable means from whichever angle the signals comes from the radar, how this little performance you can improve. So that is our work. So that is already a published work. Not let us go into the design of these things. It is a two-layer kind of design. First, let me tell you, you have to place this system, whatever I'm showing, in front of a radar, so that your system remains protected. So this brown part is the copper, and the bottom part is a substrate. Some different microwave substrates are available in the market. Some space qualified and defense qualified. So this substrate is called a Roger articulate substrate. So this is a typical design of one layer, and this is typical design of another layer. Now, how it works? It works like this. If you see this particular structure, whenever electromagnetic wave falls, electromagnetic wave has got two components: electric field component and magnetic field component. In the central part of this metallic structure, this is a metal. The central part of the metallic structure, it's a capacitor-like structure. If someone has read capacitor, you have seen that capacitors look like this. It's a parallel plate capacitor-like structure. Although it is not a parallel plate capacitor, it works like a parallel plate capacitor, but it's a printed circuit board. So what happens is the electromagnetic wave electric field component whenever electric field component gets to this part, comes to this part, it gets coupled. So that's why it makes a resonance. Resonance is a phenomena that you'll be learning when you will be going maybe 12th physics, or after that you are doing engineering, electric engineering and electronics. So this resonance cause, this is the final structure you see. So from the top layer, this resonance will cause electromagnetic wave to remain in this structure. It doesn't get deflected. Now also, if you go to the another slide, you'll see that in yellow colors of lamp resistors are used. Why it are used? Because you know that the energy principle, conservation of principle, you cannot destroy energy, or if you cannot create energy, you can only transfer from one form to another. So whenever electromagnetic signal is coming and it is being coupled to the capacitor, signals are coming. That means they have got some energy. How to dissipate energy? The resistors are used to dissipate the energy. Whenever electromagnetic signals come, some current will be induced, and that current, when go through the resistors, you know, in the Ohm's law, it will be getting dissipated in terms of heat. That is why resistors are used. And in the bottom structure, it is designed in such a way that in this particular frequency range, that was the requirement, around 6 gigahertz, it will be giving some kind of window kind of thing, so that you can have your own communication. But in the lower range, like this 3 to 5 gigahertz or 7 to 9 gigahertz, you can see the reflection and transmission is both very low. Result minus 2030 means it is very low. So that means in this frequency range, your system will be absorbing the incident electromagnetic wave. So the overall system acts like an absorber for a very wide band of frequency, but it gives some frequency band where your system or your antenna system can communicate. This is the experimentation of current plot. You see here, you see this is the resistance, but most of the current, you see the red part means high current and blue part means lowest current. This is the scale that have been plotted. So most of the currents are being here close to the resistance, so that you can understand that electromagnetic field is being dissipated in the resistor in these two absorption part. This is the transmission band part where I said that the system will be able to communicate with other. Here you see that current is only accumulated in this four part. They are called DLC. I'm not going into this, but the resistance part remains unaffected from the current. So that is why much dissipation doesn't occur in this particular frequency range, so that you can communicate by your own. This is the circuit analysis part of this. I don't think that will be much relevant for you. Let me show you some typical result. Okay, so this is some modification that we have used, because the DRDO, the defense system, they are wondering that if you can make the system active. Active means Is it possible to switch off or switch on? That means whenever you want the transmission band, we switch it on, and whenever you do not want to communicate, we switch it off. So we modified the design for the new idea of using some PIN diode. These are called PIN diode. Don't know whether you know this pin diode or not. This has got a typical switching characteristic, this pin diode, by using some applied voltage. So again, circuit part should not be there. So this is the two mode of the structure. The same structure, if you apply voltage to the pin diode, then it becomes on, switch on. So in the switch on, from the circuit analysis, we can explain theoretically and experimentally also it is true. We can see that simulation and measured both result are given there, experimentation result and calculated result, that the reflection transmission is low in the entire band. That means here it's a complete absorber kind of nature it is showing. But whenever you are making this pin diode off, this kind of window is appearing, which will be required for our own communication. So that is how the reconfigurable absorber works. This is the advanced absorber, reconfigurable absorber, that is being used in the 4.5G aircraft systems like Rafale or Su-37 or Su-57. These are the advanced version of the system where this kind of radar observers are used. Okay. No need to go to the analysis part. You can see the fabricated one. This is the experimental prototype that we designed, developed before testing. Let's not go much inside of this theoretical part. Okay, one thing I want to show that how can you make it the system flexible, because if you want to put it in the front part of the aircraft system, then this kind of design is required. So we use some foam, which property is close to the air property. Inside of this top and bottom layer, the foams are being placed, and in these particular things, you'll be able to make it bended. So you see the structure. This is the complete structure, the bending structure, and the measurement is done in anechoic chamber. So this conformal part, that is the flexible part, was also working properly. I'm not going into theoretical part and other technical details that might not be relevant. Let us come to another work very briefly, and we'll be finishing. Multifunctional, what is multifunctional? That is the most advanced type of thing. F-22 Raptor or these things are using this kind of system now. It has got two kind of option. It will have multiple functionalities, as the name suggests. You can understand that sometimes it happens that your frequency of operation is leaked to the hostile system. Your enemy country knows that in which frequency you are operating. So they use a particular jamming radar to that particular frequency. In that case, you have to do is that you have to continuously change your transmitting frequency. So your window should also be continuously changing. So this is particularly, you see this diagram, we have to design some kind of system where both absorption, upper and lower absorption parts are there, but some form of transmission band is there where the frequency is changing. Now, another requirement is that also in some time you need to communicate also. For the communication, you have to run your own antenna system, and for that notch band means very high reflective band, so that you can use your own antenna. The problem is twofold. First is that if you reduce the entire reflection, it will be fine, you will not be getting detected, but you cannot operate by your own. And on the opposite side, in the contrary, if you increase your reflection, your own communication will be very nice, but you will be easily detected by the hostile system. So how to make a balance from this? So if you can make this kind of system where you can switch off and switch on. Previously we just switched off and on the transmission band. In this system, if you can switch from transmission to notch band, or notch to transmission band is possible. Physically understanding, you can switch your transmitter mode or receiver mode by your own while operating your radar system is possible, then it becomes very helpful. Additionally, if you can continuously change your frequency range, then chance of getting detected by the hostile system gets almost minimized, because if they knows what frequency you're operating, you are continuously changing your frequency. So that problem is also being resolved. So I'll just show you the structure and finish it. This is the top and the bottom layer of the structure. Here we have to use varactor and pin diode. Pin diode, we just know that can be used for switching purpose. It can give capacitance and resistance by applying voltage. And varactor diode is that by applying reverse bias voltage, you can continuously change its capacitance. So these two diodes are put over here. Why this structure is chosen? If you ask, that is from you have to do circuit analysis and synthesis. So that is not within the scope of this discussion. But we have done the circuit analysis, designed the circuit, and synthesized this particular structure. This is the most advanced form. That was the last published work. Most advanced form. You see, these are the circuit analysis part what we designed. Coming into the result, you see this is the result of the structure. Whenever the off state is used, you see the absorber here. As I said, when transmission reflection both low, absorption is occurring. This part absorption is occurring, and only in this frequency range high transmission is there. The same structure, if you just switch on the pin diode, you can make this transmission band in reflection band into a reflection band. You see, this is a reflection band. Here a very high reflection, but in the other upper and lower side, low absorption is maintained. So that problem is getting resolved. Second thing is that continuous changing of frequency. I'm coming to this. Let me show you the change of frequency part. First, this is the result. You can see that even in transmission band, you can continuously change while maintaining low absorption in lower and higher band. And the notch band also you can continuously change. You see the voltage I have mentioned here, whatever the voltage you are applying to the varactor diode. If you apply the varactor voltage to the varactor diode, you will be getting this kind of change of frequency. So by this way, you will be able to change your operating frequency so that you're in both cases, in receiver mode, that is in transmission band, and in transmission mode, that is in reflection band. All this frequency can be continuously changed. Now this might be looks interesting. This is the fabricated system. The entire system we have fabricated this structure. You can see this wire bias line. As I said, that pin diode and varactor diode reduced, there is voltage supply voltage like 10 volt, 15 volt that I had shown. So these bias lines, from the bias line you can provide the supply voltage. This is the fabricated prototype. Another thing, this I just want to mention, some of you, if you want to become designer, electrical engineer, electronics designer, you see this is the biasing strategy that we have developed. This is also a unique biasing strategy. This kind of strategy was not available, because the problem is that in aircraft you cannot simply increase much layers, so that aircraft will be heavy and your speed will be reduced. So that is also a requirement. So this is a biasing has been done at 2-layer biasing. All the 4 structures can be biased within the 2 layers. So this is a new biasing methodology that actually we have developed. You can see the methodology where we have given one common port for the biasing and other ports are being as a reference voltage. So the both layer we have used the same biasing strategy with little modification. By this way, without adding any initial additional layer, you can see that we have not added anything extra over there. The structure is able to perform its operation. So I think that is fine for today's discussion. Many things are too much technical, so I'd be happy if you have any questions over there.
Thank you, Dr. Bakshi, for
Sir,
your.
please stop your sharing.
Yeah.